Hello. There we go. The joke for today. What type of sandals do frogs wear? Open-toed.
Good morning, everyone. Welcome. Hopefully you're enjoying the weather. It's nice. It's pleasant. It's a little chilly, but look, you get to step outside and not start sweating. That's like, no, you would not. There's no way. Yeah, this is taste of the. We don't have fall. Taste of winter. Yeah, I don't know. It always brings back fond memories of me. Every time it gets cold like this. So, anyway, hopefully it brings back fond memories for you as well, or at least you get to use part of your wardrobe that you never touch. This is the first time I've worn a jacket since what was it, May? And I say May because that's when I taught high school. My high school was so cold I always had to wear a jacket. So, anywho, so last week we finished up work in kinetic energy. Hopefully you all, reminder, if y'all didn't finish the lab, just try to get that done by like today, tomorrow. I think most people are almost done with it. It's largely, if you did the things, you're good to go. We're not going to be nitpicky with this. The lab went a little long, which isn't ideal. And so this week's lab, or Tuesday's lab, is going to be a little bit shorter, so it'll even out. Anyway, the stuff we're getting into this week is much easier. So we kind of did the hard stuff, and I say hard stuff with a very, anyway, like work in kinetic energy. Work was kind of like the tricky part of energy. Potential energy and conservation energy is going to be really easy. Conservation energy is something that's like super easy to do. I say super easy. It's very straightforward. Very, very straightforward. Very, very useful. We've kind of been doing it this entire time. But now we'll just kind of look at the equations a bit differently. So, it's fairly straightforward and fairly simple. So it's going to be great. So we're going to talk about potential energy. Then we're going to talk about potential energy work. Starting energy, this phrase, explain that starting energy must equal final energy if no energy is lost/gained from the environment. I'll add that because that's, and then demonstrate energy exchange. It's stuff we've already been talking about. It's just another way of looking at energy. And it's what I start with is what I end with. If it's not what I end with, work was done. That's it. Like it's great. It's so straightforward. All right, here's things you all need to remember from before. It's stuff that hopefully you know. Gravity is negative 9.8. When we plug gravity in, we are going to put the positive, but I just put the negative here as, let's even just put G equals positive 9.8 here. Because it's the value of G, not necessarily the exact, whatever. We'll put it as positive here. All right, force due to spring is Kx. What is work? Kinetic energy equation. The things we covered last week. Boom, great. Okay. Things you need to know from last time. Hopefully all of this isn't a surprise. If it is, I'm surprised. This is all stuff we've seen quite a few times at this point. All right. Okay. This is important. We've been talking about this, but just to clarify this, when you're talking about energy, we kind of mentioned this, you have to say what your system is. You have to say what you're focusing on. What is the thing you care about? That's the system. Everything outside that is the environment. It's a really important definition. You're going to see it used a bunch. You got to say, what am I focusing on? And then you're doing everything with that. And then everything outside that is the environment. It's really important definitions. And we've been using this. We've been using this with work. So it's not kind of a new thing in that way. Remember when we looked at like the various things, like the elevator. The elevator was a system we cared about. Or we looked at a box going down a hill. The box was what we cared about. If you look at everything in the entire universe, nothing changes on average. The entire energy in the entire universe stays the same. The entire momentum in the entire universe stays the same. The net force in the entire universe is 0. You have to look at a piece of it, and that's when things change. And that's where obviously we don't look at the entire universe. Unless you're doing cosmology stuff, then I guess you look at the entire universe. But the vast 99.999% of cases, you look at a piece of it. You don't care about the entirety. And you got to define what that is. What am I looking at? It's something you will probably do intuitively. This is just the vocab to match that. System is what you care about. Environment is everything outside the system. And they interact with each other. Makes sense. You could say, like, I'm the system and everything around me is whatever. Hopefully that makes sense. All right. Okay. The system is not isolated from the environment, and they always interact. So either the environment is adding energy to the system or taking away. We will do some ideal cases, but the reality is they always interact. It is impossible to fully isolate something from the environment, i.e., it's actually impossible not to gain or lose energy to the environment. It's just not going to happen, y'all. You can't have a perfectly efficient system. Absolutely impossible. So perpetual motion machines are machines that like go on forever and ever and ever and gain energy. That's nonsense, unless they're getting energy from the environment. A system can't just gain energy from nothing. It gets it from the environment. Pretty much any perpetual energy system you all see, it's a cheat. It's stealing energy from the environment. But it's also impossible for a system to never lose energy. It's just going to happen, y'all. There's always some friction or radiation, or even in space. If you're floating in space, you are radiating heat out into space. So even though there's no air around you to cool you down, you will get cold because there's radiation. You all emit infrared radiation. You eventually get cold. Heat is actually a problem in space. You have to get rid of heat, which is a really interesting thing. So space stations, they're not actually concerned with staying warm. They're concerned with not getting too hot. If you have anything in a space station, it has to have some way to radiate extra heat away because everything generates kind of waste heat. Anyway, fun things to think about. There's cool stuff with that. All right. Fantastic. One of these questions that like you probably know the answer to. Hopefully you know the answer to. If not, that's fine. I'm going to teach you. How does an object gain gravitational potential energy? Not a trick question. And to clarify for part C, slide it on the ground means flat ground. Flat ground. How long do we really want to? I'll go to a minute. I mean, either you know it or you don't. And if you don't, that's okay. All right, 5, 4, 3, 2, 1. All right. So, again, this is foreshadowing. You have probably learned, maybe, I don't know. I feel like a lot of people have learned this. There's two symbols for potential energy. So potential energy we're going to learn, you can write as PE, and we can put like a little G next to it for potential energy due to gravity. Or we're going to see in this class using the letter U. I do not know why we use the letter U. No idea where the history behind that is. But that's a common letter that's used for potential energy, and we put a G next to it for gravitational potential energy. You know, it's a fun, y'all can look up. Anytime there's any notation and it doesn't match the letter, there is a reason. Someone at some point had some logical reason why U matches potential energy. I don't know that reason off the top of my head. Anyway, this is the equation for it. This is what we're going to discover together in the next 2 slides. We're going to derive it from the work equation. But there you go. How do you make it gain it? You either make it gain mass, which that was none of the options. You increase the gravity. Good luck. That's a really hard thing to do. You basically have to go to another planet or get closer to the Earth. Well, and that's the last one. You change the height. So boom, lift it higher. Fantastic job. This is an equation you've probably seen before. But what's going to be new is we're going to derive it, and we're also going to relate it in the derivation. It's going to relate it to work and all that kind of stuff. So as before, here's the equation for the derivation. So we start with work. The equation that you all have work equals, and in this case, they got rid of the cosine theta. They're saying, so this is actually a good clicker question. You know what? Yeah, I'm going to stick this here. I'm going to make up a question right now because it's we'll pop back to that. So I'm looking at this. Work equals the integral of f dx. So I'm going to copy and paste that. And I've decided to make a clicker question on this right now before we go any further. If work equals f dx, is the force parallel to the direction of motion or anti-parallel to the direction of motion? So parallel, anti-parallel. Because I kind of just put it there and it's fine, but I want to make certain we don't just skip over this. If work equals the integral of AB f dx, is the force parallel to the direction of motion or anti-parallel? I.e., well, and I'll show you all the other way of thinking about this. Cosine of the angle. Is it positive or negative? So the negative and positive should only really come from the cosine of the angle. So in this case, everything's kind of assumed to be positive. So we'll say it's parallel. And if we really want to be nitpicky, we'll put some absolute values around those. I say nitpicky. We really want to be accurate with our wording.
Oh, parallel. For some reason, I was thinking perpendicular.
Okay. No. All right, I'll give you all like 10 more seconds. I think pretty much everyone's answered this. But this is just testing us because there's something left out of this equation that was kind of done in the background. So 3, 2, 1. All right, so I think we all did pretty good with this. All right, largely good, but I'm still glad we asked it then. That's enough that it was worth doing. Remember, y'all, that work equals the integral of f dl. Oh, that's a good question. If you pick, I'm just going to hope it was a fat finger situation. Hit the wrong button. Either way, how do we decide it's parallel? Remember, positive or negative comes from the cosine of the angle. That's just really what I want to keep reinforcing with you all because it's one of the most common mistakes and things like that. So in this case, this is positive, which means cosine of the angle is 0, which means it's parallel, which means energy is getting added to the system. So in the case of gravity, that means it's falling. In the case of gravity, this is falling. Anyway, it's just important to mention. All right, great. So there it is. Then we're just going to replace F with m times. You actually have already done this. You all have derived the equation for the gravitational potential energy. We've done a few problems where you've derived this yourself. Maybe you didn't even realize it. So F equals ma. Great. A is g. Great. Those are all constants, so they get pulled out to the front. All right. What's the integral of mg dy? We use dy because you always choose the path you're taking. When it comes to gravity, you're going up and down. That's the only times it matters. To clarify to y'all, just remember the equation. It says dl. dl is just whatever path you're taking. That could be dx, dy, dz, dr. You just kind of put whatever the path is. You put that variable in there. dl is a general variable for the direction you're going. All right. A little less than half of us are not correct here, so be careful. Write out this integral on a piece of paper and actually write it out because half of us are not quite right on this. Which means you're making, if you're making a mistake in here, it's going to be a silly mistake. And if you write it out, you won't make the mistake. Write this out as just a normal integral like from a calc class. We have m, which is a constant. G, which is a constant. Dy. Check with your neighbors. See what they put. That's one of the best, it's pretty much the best way to check your work is to ask someone else. There's a reason group work is so prolific, like so common in the workforce. More efficiency, less errors, all those things. All right, we'll go for like 10 more seconds or so. All right, in 5, 4, 3, 2, 1. All right, so let's just do this integral, y'all. So pull this down. So work equals the integral of y initial, y final, mg dy equals, m is a constant, g is a constant. Pull them out. They're constants. You can pull them out of the integral. Y initial, y final, dy. What's the integral of dy? Just y. The integral of dy is y. So there you go, and you plug in those bounds, and we get mgy final minus mgy initial. Ta-da! There, you just derived the equation, mgh. If you just replace, so we can instead write this like this. Mg delta y is literally how much you move up or down. There you go, that's my change in energy. Look, you all derived this equation that you might have seen in middle school or high school, MGH, ta-da, now you get to see where it comes from the work equation. This is why I taught you all work first. Every single energy equation is derived, all the ones that we're using are derived from that equation. Kinetic energy, we derive from the work equation. Potential energy, we derive from the work equation. Energy stored in a spring, we're going to derive from the work equation. They don't just come out of nowhere, y'all. They're not actually even from measurements. They're from that one equation, and everything stems from that. So anyway, woo. There you go. Okay. How high up are you right now? Are you 0 meters high, 3 meters high, 6.31 times 10 to the 6 meters high, or negative 10 meters high? And before I forget, you can ruminate on this. It is that time. My phone reminds me to take attendance. And Leo gets his steps in. Boom. Boom. Look at it go. That's a great question. It's not defined. Not defined. Up to you. You decide. You've gotten to the heart of the problem. Oh, nice. You got to the heart of the problem.
Nah, brother.
Million joules of energy. Unless you figure out where to go. Yeah, no problem. All right. As always, Leo's got you. If you need him, call him over. Ask him how he's doing. All And at this point, I'll close it. If it didn't work for you, contact Leo. All right. So I'll leave this up for a little bit longer. It got sent to your all system. Leo, you got someone behind you. All right, I'll give you all a little bit longer. Don't overthink this. Go with your gut. There is a right answer. There is. And, well, that sounded singular. All right, 3, 2, 1. They're all right. Every single answer is right there. Reminder to you all, position, height. How high up are you right now? That is a measurement of why. That's a measure of your position. Remember, position was relative. That was one of the first things we covered in this class. I asked you, hey, where's Demo Duck right now? And the answer was, depends on what you reference. If you reference your chair, if you reference, you could be the reference, at which point you're at zero height and everything is relative to where you're located. Or you could say the reference is the second floor of this building, in which case 3 meters is right. Or you could say that the reference is the center of the earth. That's about the radius of the earth. Or you could say the reference is some random location 10 meters above you. You can be negative 10 meters high. That just means that 0 is above your head. What does all of this mean? If height is relative, potential energy is relative. When we talk about energy, if I told you I had 1,000,000 joules of potential energy, that does not tell you what's going to happen. You have to know about the potential. You have to know whether or not there's a place that can go lower or higher. Energy is all relative. It doesn't really mean much to have 1,000,000 joules of energy if everything around you has 1,000,000 joules of energy. Nothing's really going to happen. So it's all relative. It's all relative. Height is relative. We generally define sea level as 0, but that's not a requirement. You can pick any 0 you want, and the problem will work the same as long as you're consistent in the problem. We're going to see that. We're going to solve some problems where it's maybe more beneficial to choose different things as 0. But there you go. This is the energy associated with an object in a gravitational field. And we're going to learn that everything wants to go to lower potential energy. That's like a law of the universe. Everything in the universe, if it can, it will go to lower potential energy. It explains like everything. Everything on a tiny scale. It doesn't explain you as a person because you're too complex. But charges, they want to go to lower electrical energy. Things with mass want to go to lower gravitational potential energy. Every single thing that happens in this universe, you can basically say, why does it do that? It's trying to go to lower potential energy. At least on a very specific scale. It doesn't explain why people do bad things. That's more complicated. But physics things. Specific physics things. All right, and yeah, G can change. You're on different planets. This equation still works. Other planets also have gravity. Every single one of you is making a gravitational field. We're going to learn about that in 2 weeks from now. Every single one of you is making a gravitational field around you, which is affecting everyone else in this room. So every single one of you is getting gravitational energy from every other person in this room. It's not very much, but it exists. If you all were floating in space and there was nothing else around you, you would eventually start going towards each other. Everyone is attracted to everyone. There you go. Whatever, we'll get to that. But for now, just know that G can change. Like on Earth, great, 9.8. Positive 9.8. Positive 9.8. Do not put a negative in this. If you put a negative in this, it's going to mess up the math. Remember, we don't put positives and negatives based on direction for energy. Don't do that. It's positive. Every time we work with energy, how do you define whether it's positive or negative? From the math. The math will tell you, not the direction of things. All right, cool. I believe in your abilities here. Fairly straightforward, just to kind of test if you know what you're doing, if you know the right units. What is the gravitational potential energy for a 10 kilogram object that is 5 meters above the ground? And I'm gonna tell you the reference. The ground is 0 potential energy. I have to tell you the reference, otherwise the answer could literally be anything. Well, it could be 2 of these answers. But in this case, there is 1 right answer. 2 of these answers are wrong no matter what I put in this problem. You probably saw this in the test. I do ask questions with different units. Units matter. If you order a sandwich, you don't want to get a hot dog. You can argue that. But the units matter. Check with the people around you, but we're looking pretty good. All right, we'll go to like 135. All right, 5, 4, 3, 2, 1. All right, we're multiplying, y'all. We've grown 50% since class began. All right, what's given? We got mass. We have H. What are we solving for? Potential energy. What's the equation? MGH. So you just multiply 10 times 9.8 times 5. And 10 times 5 is 500. Nope, 50. 50 times 9.8 comes out to 490. And then what's the right unit? Well, you can figure out what the right unit is by hopefully remembering what the wrong unit is. Newtons is for force. Like, just remember from your last test, newtons is force. Well, that's not energy then. So, boom. Joules. Every single type of energy is joules. Work is joules, because that's how much energy you gain or lose. Kinetic energy is joules, because it's energy. Potential energy is joules. Energy due to heat is joules. Energy due to friction is generally kind of heat. Energy loss due to friction. If the word energy is there, it's joules. It's all joules. It's all joules. Yeah, there's other units for it, like calories, but we're not going to bother with those. Yeah, when you all are eating food, if you all look at the box and it says how many calories it is, that is a measure of energy. That's the energy stored in the food. They determine that energy by literally burning the food and seeing how much it increases the temperature of water around it. So when you all look at a food box, the calories is another unit for joules, which is kind of cool. And they literally just burn it and see how much energy gets released. All right, now let's derive another equation, the one for a spring. Oh, look, we start with the work equation. We actually did this in the problem in the last class. We replace the force of a spring with Kx. We then integrate it. All right, what's the integral of Kx dx? Again, all these equations for energy, they're not just out of nowhere. That's so much of the fun of physics. You're getting to learn literally how everything works, starting with just literally observations of reality and going from there. Nothing is out of nowhere. I mean, I guess you can make arguments that observations of reality. Well, no, that's not out of nowhere. It's not a word. Whatever. Think of it how you make. But that's what's so cool about physics to me. We don't skip any steps. And we get to learn about how the universe works. And it's exciting. And so for whatever reason, for me, it's just super cool. Yeah, I'll go around if you're stumped. Write it out if you're stumped. It's just a math problem. K is a constant, y'all. It's a spring constant. How come? How come? Good eye, y'all try this. Alright. I'll give you all like 15 more seconds. It looks like we're pretty much there. And 5, 4, 3, 2, 1. All right. So great. So work equals the integral of x initial, x final, kx dx. Again, there's secretly that cosine theta. In this case, a spring is we're going to say it's pushing the same way it's moving. Fantastic. All right. Pull the k out. K is a constant. It's literally called the spring constant. X dx. And the integral of x is x squared over 2. Power rule, I think, is the name of it, or something like that. Great. Kx final square. Let's write this a little nicer. Pull the 1/2 out. 1/2 kx final squared minus 1/2 kx initial squared. And if we just set the initial as like the equilibrium position, ta-da! You derive the equation for the energy stored in a spring. If the x initial is 0, then that term goes away, i.e. the equilibrium position. And this is if I stretch a spring, this is how much energy is stored in it. And if I release it, it will convert this generally into kinetic energy. If it's stuck to the spring, it'll kind of go back and forth. It'll convert to kinetic and then back to potential and then back to kinetic and then back to potential. And that energy will generally get lost over time. The spring doesn't wiggle wobble forever. It loses energy to friction. If it was possible, if you had like a little heat camera and you watched a spring that was kind of wiggle wobbling, you would actually see it getting warmer over time. Very, very tiny amounts. But, and that gets interesting. Why is that? Because you're like straining the crystal lattice of the molecules, and then they kind of get compressed back. That releases heat. That makes them start wiggling. So you pretty much always lose energy to friction, y'all, of some sort. And it's pretty much always heat. Heat is the heat death of the universe, right? You all have heard that. Everything gets turned into heat and it all gets spread out, and eventually everything will just be a big constant heat everywhere. But that's so far.
The distance from equilibrium is how much is compressed?
Yeah, it's a good. Yeah, the distance from equilibrium. So if we have like a spring just chilling, let's just have a spring sideways. Nothing is stretching it, and then if I stretch it, this is the x. So x is equilibrium is if nothing is pushing or pulling it, if nothing is stretching it. I put it sideways on purpose. If you actually hang a spring, it will stretch because the weight of it will pull the spring down. So we have to do it sideways. X is how much it gets stretched from its resting position. And K is something you either calculate or is given to you. This number can vary wildly. Like the spring constant can be like 1 Newton per meter all the way up to like thousands or tens of thousands of newtons per meter. Case in point, let's look up real quick. Spring constant, a really common one is a garage door. Spring constant of garage door spring. Those are wicked strong. So I'm just hoping it pops up here, but it's not. That's very sad to me. All right, well, that's weird. I'll look it up later. So if y'all have a garage, there's a spring in it. And this sadly did not tell it to me. I was hoping it would just pop up. I'll look it up later. It's wicked strong, y'all. You do not want to do work on that spring unless you have the right tools and the right safety measures, because the spring involved in those garage door things is just like, it's a lot. There's a lot of energy stored in that spring. And there's various springs related to that. The spring constant on, you all have cars, well, you may or may not have a car. If you all have springs as your shocks, those are also fairly stiff, also have very, very high spring constants. And then there's tiny spring constants, like the one inside of a clicky pin. There's a little spring in there, and that's really, really weak, so you can push it. So engineering-wise, how do you choose a spring? It depends on the job. Like, if you need a stiff spring, choose one with a high K. You need a not stiff spring, choose one with a low K. It's a really, really interesting engineering thing. Tons of different, some springs you can't even compress, because they're already compressed. Like, you have to make those decisions as engineering. That's where we go from physics to engineering. Great, here's a spring. In the real world, you got to choose a spring for the job. What's one that's going to accomplish the job you want? You got to actually think about those kind of questions. It's a whole different way of thinking than, it's a different problem than a physics problem. It's more of a practical, hey, I need to do this. What does that? All right. Okay. The relationship between work and potential energy is work is the negative change in potential energy, which is opposite. I'm going to remind you all. work is the positive change in kinetic energy. So they differ. And this is actually not too difficult to derive. We'll just do it with gravity. I don't think it's the next one, but no. We can prove this really, really simply. Really, really simply. We'll just put numbers in. So to derive this, let's just look at gravity. Work equals the integral of F dl times cosine theta. Work also equals potential energy equals mgh final minus mgh initial. All right, so we're just going to calculate those two things. Let's say we lift an object from y equals 0 to y equals 1. That's the problem we're going to do. And we're just going to prove this relationship by making up a problem. Okay? So if we do that, this equation is really easy. It's just mg, right? The change in potential energy is that. Great. All right, let's do this equation. It's going to be the integral of mg, magnitude of that, times dy, times, and this is where you got to be, we're immediately going to see why this is the case. If I'm lifting something upwards, so I'm lifting, the thing is going up, which way is gravity? Down. So if Fg is down and the direction I'm moving is up, what's that angle going to be? 180. What's cosine of 180? Look at that. Now you see why they're negative. You get a negative when you go opposite of gravity. So when you're lifting something, gravity does negative work. When something is falling, gravity does positive work. That's literally all that says. That's where this comes from. All right, so if you're like, why is it negative, whereas the kinetic energy was positive? It's because when you lift something, you're going opposite the direction of gravity. And you get a negative sign. That's it. Okay? So I just want to point that out. If that doesn't make sense, that's not a huge deal, but it is really important that you all know that it's negative and the one for kinetic energy is positive, because we're going to use that to derive conservation of energy. Everything gets derived from work, y'all. Literally every single equation is derived from work equals integral of FDL. Everything. Even conservation of energy. Something, again, you probably learned before at some point. All right. Try it out, y'all. Find the force corresponding to the potential energy. Write down your givens. Write down what you're solving for. Find an equation that relates those two things. And see if y'all can figure it out. It's a fun puzzle. Which way do we want this thing to move? What kind of piece? We'll figure it out. I don't know if I need to tell them the direction or not. I don't think I do. If you move in the positive X, we'll see what happens. We'll see what happens. See if I need to tell them whether or not theta is 0 or theta is 1. It just changes the sign. And to make this so you don't have to worry about things too much, find the magnitude of force. So now you don't need to worry about directions. You don't need to care about whether it's in the positive direction or negative direction. I'm not asking you what direction is force. You actually don't have enough information to determine that. Yeah, if you're stumped, write down the givens. Write down what you're solving for. Is there an equation that relates these things together? It's going to be some of the equations that we just went over. Kind of jot those down and see if the pieces will start to kind of connect. It's more exciting if you make those connections than if I tell you the connections, so that's why I'm not giving too much away.
Just today.
I love that. I was like, that's
I didn't even.
no, you're good, man. I was thinking about the whole time. You are ready.
Need to get my calories.
Yeah, dude, I mean, peanut butter is probably like one of the best protein foods to have. Cause like, how many calories is in that entire food? Peanut butter is so dense in calories. Like in a good.
33 times 190.
Yeah, I was like that last dude. I was like, you can survive on that for. It's got so many good things in it. Yeah. Well,
Literally.
they eat 2,000 a day. So 33 times 190. Yeah, sure. Yeah, sure. Some need more. Some need. Yeah. 3 days worth of food. That's pretty good. I mean, look how. That's pretty efficient. I mean, if you had to just eat peanut butter, that wouldn't be. But you would survive. I mean, you'd survive for 3 days without food as well. But
3 days more.
so much energy, such dense energy. All right, you all figure out the puzzle. What do we have? Always right. And then, what are we finding? What equation do you think have that would like anything in like?
Yeah, I know.
There's only one equation you can have with what is
Just the magnitude, ignore the cosine, right?
Because it's finished getting rid of it.
That tells you direction. And in this case,
Oh,
what is
wait a
your
minute.
dr?
You can just
The function here is given.
It's actually one of the ones we saw.
It's r.
no way, no.
So it would just be x, right? You're defining your position in terms of x, essentially. Yeah. So you've got the integral of f dx is equal to.
That's the key to this. Is just realize there is kind of two things you gotta relate to each other.
The other side is just that.
No, okay.
Do you mind if I write it down?
Okay. Well, work is defined as. So there is a relationship between work and potential energy. What is that relationship?
So if I have to find out what would, which is the opposite.
If y'all are stumped, I'll go back to the last slide real quick to remind you a relationship that's probably going to be useful. Well, probably. Definitely. Work is the negative change in potential. Alright, so now we got a relationship between work and that. And I'm going to write this a little different for you all. So this was a over a big change. What do we make it if it's over a small? This delta, what does this delta turn into when it's a really small change? It turns into D. With respect to, what is my energy changing with respect to? How do I make potential energy change? Gravitation potential energy. How did you all make that different? What variable does it change with respect to? Height. X can be Y, can be Z, can be whatever direction you're going. These two things are the same thing. They're the same thing. If you make a change really small, it becomes a derivative. That's all a derivative is a change. That's really small. All right. So u of x equals negative a over x plus b over x squared. What are we solving for? Magnitude of force. Step 3. We just said that this is a thing. And I'm going to see if you all can figure out, there's one more equation you all need. Nowhere in that equation is force. See if you all can find an equation that relates one of the things that we're going to find to force. It's one we've been using a lot. Holler if y'all are stumped. Holler if y'all are stumped. If you can't figure out that next equation, it's one that you all did last week a lot. What is it? Hey.
Yeah. I mean, do you have that? Oh, I see.
Work is defined as in.
It's all related variables to variables, like equations for equations. No, there's another
Skip that.
Yeah. Not so much. So physics 3, not so much. Physics 3 just but upper level physics
Looks different from
because you can solve the expression. You can do that for any
If you want to find a work,
No, those are constants.
work is. I'll be just work is.
Exactly.
Yeah, bro. Forward.
Oh, yeah.
Yeah, bro. Forward.
I was like, really? You want to try that? Because if you get the work, so you get the work, and then I get how do I get rid of take the derivative of this? Oh, so you don't need that before. Because the derivative would give it All right.
Well, this is changing you.
So that's saying if you want to go, if you have an equation of potential energy, take the derivative of it with respect to x, and that'll give you the work. So that's still work. Okay. So good. Yeah, and with the negative sign, right? Yeah, that's important. All right, so what's the relationship between work and force? It's the one we did last week. I believe in you. Work equals force times dl times cosine of theta. It's magnitude, so you could just pick theta to be 0 in this problem. All right. Let's just try it, y'all. Let's just see what happens. Look, we have a relationship between all the things. They're all there. All the things are there. If you're like, so at this point, if you see that all the variables are there, because look at this. We know u, so we can put that here, which lets us get w. And by getting w, we can put that here. And if you're like, what do I do then? Just try it. Just start plugging things in and see what happens. Sometimes just starting, if you have this setup where you have all the relationships, sometimes you just got to start putting things in and see what happens. So go ahead, do the first step. Find the work. So work equals negative derivative with respect to x of negative a over x plus b over x squared. To clarify here, x is, or a and b are constants. A and b are constants. So do that. Find the work. It's just a derivative. This is just math. The physics has been done. Steps 1, 2, and 3 is all the physics. Step 4 is just doing math. There's no more physics in this problem after you do steps 1, 2, and 3. So derivative of this is going to be, the negatives are going to cancel, but then you spit out another negative. Negative there, but then the negative spits out another negative, so that ends up being plus 2b over x. Great, that's work. We're not done yet. Now do the next step. Plug that into here. So negative a over x squared plus 2b over x cubed equals the integral of f. And we're just going to go ahead and change dl to dx because it clearly seems to be dependent upon x. And we're just going to decide to make theta 0. It's magnitude, so we don't really care. I asked for the magnitude of force. I'm not really caring about the direction and things like that. All right. So, this got a little messy here. Okay. All you have to ask yourself now, you're like looking at us like, what do I do? What's the opposite of an integral? Take the derivative of both sides. That's all you had to realize for this last step. An integral, so it's like an algebra problem, but you just have to realize algebra is all about doing opposites. The opposite of an integral is a derivative. How do I get rid of that derivative? I take the derivative again. And I forgot a negative. Take the derivative of both sides. Remember, anything you do in algebra, anything you do, boom, integral's gone. It'll also get rid of that dx for you. So it just gives you f. If I integrate with, and in fact, I can show you all, this is kind of a hand-wavy thing that people really don't like. You can just divide this dx to the other side, and then that's a derivative. It's d dx. It's a weird thing. But for now, just trust me, if you take the derivative of this, it gets rid of this integral and this dx. That's how that works. The d gets rid of the integral, the dx cancels with the dx. There you go. All right, and I'm going to mosey around. The answer is something. Yeah, I'd have to actually. Nope. Answer negative 2a over x cubed minus 6b over x fourth.
I think one of them has to be a different sign.
Oh, yeah. Yeah, you're right. I forgot to put the negative down here. My negative got lost. Yeah, there you go. And the negative is still kind of tricky to see. So this problem, while it looked kind of weird, it was just relating variables to each other and then doing some calculus algebra. I don't know, it's kind of interesting. Teaches you all how to work with these equations. That's what this lets you, that's the purpose of this problem. It teaches you all how to work with these equations when calculus is involved. It's a weird force. What does this correspond to? I have no clue. What real world situation is this? No idea. But the cool thing is if you find an equation that for the potential energy over time, or the potential energy over distance, you can find force from that. That's literally all we need to know here. Anyway. All right. Okay. So moving onwards, now we're going to get into conservation of energy. Have you all noticed we're already like, I don't know, it doesn't look like, we're pretty much almost done with this. Conservation of energy is really simple, which is great because it'll give us more time for momentum. We'll probably end up actually starting momentum on Tuesday, even though we're going to do a lab on conservation of energy. It's fine. More time for momentum is good because we're going to be back to vectors. On Tuesday, we're back to vectors again when we get to momentum. Anyway, all right, this is that quote I've already told you all. Conservation of energy. You start with some energy, you end with some energy. It's the same. Okay. Derivation for conservation of energy, y'all. Really, really easy. We're going to just do it on this slide. I don't actually need to have it in writing because it's so easy. Work equals change in kinetic energy. We derived that last class. Work equals negative change in potential energy. We just derived that. They both equal each other, right? Work equals that, work equals that. So long story short, change in kinetic energy equals negative change in potential energy. Just set them equal to each other. They both equal W. If A equals B and B equals C, then A equals C. Great. Let's write this out. 1/2 mv final squared minus 1/2 mv initial squared. That's literally the definition of change. Equals negative 1/2 m. Nope. Mgh. You know what? Let's keep this even nicer. Let's not even put these equations in here. Let's just keep it in a general form. It works out the same either way, but I just really want to show you all. Kinetic energy final minus kinetic energy initial equals negative potential energy final minus potential energy initial. Nothing fancy. So kinetic energy final minus kinetic energy initial equals negative potential energy final plus potential energy initial. And through the magic of moving things around, kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial. Woohoo! We did it! We derived conservation of energy. What I start with is what I end with. There you go. Isn't that nice? And so that equation you might have seen before, you might have done, and this might have looked like this. 1/2 mv, and we just flip sides, because generally we like to put the initial on the left. So 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Again, the cool part here is you all have probably done this before. If you've ever taken physics in high school, you definitely did this. You might have even done this in like a physical sciences class. In our class, we get to see that it doesn't just come out of nowhere. It's not just, hey, here's conservation of energy, do it. It all comes from work. Everything comes from work. Which, I don't know. From one equation, there's so much we were able to do. Woohoo. All right, so there it is. Same thing, and writing in all its glory. Okay. All right, this one you're going to have to spend some time on. It's a good, I say spend some time on, spend some thought on this one. It's a fun problem. So, I'm going to straight up tell you. So if an object is dropped from a height of 10 meters, at what point is the kinetic energy equal to the potential energy? And my recommendation to you all is use that equation. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. You all are going to see me using U for potential energy. I don't know why. I know why. It's one less letter than PE. That's literally the reason I use U. It saves me a second. U stands for potential energy. All right, try it, y'all. At what point is the kinetic energy equal to the potential energy? Is it at 0 meters, 2.5 meters, 5 meters, or 10 meters? It's a fun problem. You can put numbers in. You all can totally put numbers in. It's multiple choice. If you really wanted to, you could brute force it and just kind of do all the calculations. That's great. And that key phrase to figure this out is when the kinetic energy equals the potential energy. You're going to see how we're going to use that in this equation. There's actually a couple ways to do this. It's great. Love this question.
Can you think how you would do it without plugging in numbers? If you're solving for
Oh.
Yeah.
You could just say some starting energy. So it comes out really simple. So you have some starting energy. Let's just see, kinetic energy initial. It's going to equal. Well, on the other side, you know that kinetic energy final equals potential energy final.
Yeah.
So you can just do this.
Yeah.
And so to that end, I don't know, you can make up any number you want. So it is going to be so it's going to be half the height.
Okay. That's what I thought, but I was trying to go.
Yeah, and honestly, I'm unsure. So with numbers, that's why I put that to make it easier. We know that this is going to be double this. So, to be honest, if you know this is going to be double this, yeah, it's unfortunate. Yeah, I'm trying to think through what I would do here.
Because you're solving for a height.
They're both equal to each other. Yep.
Okay.
Yeah, so to clarify this question, at what point is the kinetic energy equal to potential energy? Let's just pretend that the kinetic energy final is 3. That means potential energy final is 3. At what point are the energies equal to each other? At what point is the final kinetic energy equal to the final potential energy? So to just clarify that, at what point is the final kinetic energy equal to the final potential energy? I'm not asking at what point did all the potential energy turn into kinetic energy. Oh, I realized. Okay, you don't need the numbers for it. No, that's why.
You would just
I don't need numbers for it.
The reason. So U initial.
Yeah.
So U final. So MGH initial equals 2 times MGH final. M's cancel. G cancels. H initial equals 2 times H final.
Yes. Okay.
Yeah, and it just comes down from.
Oh, you just swap the other side instead of swapping.
Well, because at the end KE final equals U final.
Yeah.
So then that's why you have to just
Yeah.
double it. Yep. That's the way. Yeah, that's
Okay.
In the beginning. I don't know why I put ahead kinetic energy. That was silly.
Yeah, you just have the kinetic energy you put for you.
All right, I'll up your stumps, y'all. This is a good one. What are y'all thinking? So 10 meters is where it starts. What does kinetic energy when it starts? What's its potential energy? Not zero. So that's the. Always gotta back check it in certain instances. So here what happened here, it's not that the kinetic energy. So this is kinetic energy final, this is kinetic energy initial. Okay, so that's true. Potential energy final does not equal zero. So what does potential energy final equal? It equals the final kinetic energy. All right. To make this, if you haven't realized it, remember, write down all your givens, y'all. What's given in this? We got H initial equals 10 meters. There is something else that's given. It's not a number. At what point is the final kinetic energy equal to the final potential energy? Let's just write that. That is a given. Kinetic energy final equals. That's a given. That's a relationship. And see if that helps you out. That is a given. And then, what are we solving for? But that's the trick to this problem, is realizing that's a given. No, not the graph. No, we're saying at what point. does the final kinetic energy equal the final potential energy? We're just saying at some point on the path, KEF equals
So we're
0.
not solving for like right before zero.
We're solving for some
variable because
You can check these. You can brute force these. Since the answers are here, one of those right, so you can't just let it No, I guess you don't have the final thought. All right, to reveal the next kind of part of this trick, y'all. Step 3, what equation are we going to use? You know, this one. The one that's already written here. Let's simplify this, y'all. What's the kinetic energy initial? How much energy do I have in the beginning? For motion. Is it moving? All right, great. You know what else we can do? We can do, so U initial equals, remember y'all, KEF equals UF. They're the same thing. All I did and go from there. You all know the equation for potential energy. Put that in. What is the equation? Y'all tell me. Okay, what is the equation for potential energy, y'all?
Okay. So we have
MGH. Put the things in.
wait, why did you cross out the initial zero?
Because 1/2 mv squared in the beginning b is 0, so there's no kinetic energy. Rule of thumb: if you're not moving, no kinetic energy. If you're located at 0, no potential energy. V is 0. 1/2 mv squared, you get 0. No, if you define the ground as 0, then there's no potential. We're not on the ground in this problem. This problem says at what point is the final kinetic energy equal to the final potential energy. So, to draw a picture of this, I drop something initial. At some point final, and the question is, when does that happen? All right, I'll give you a few more seconds and then we'll just kind of do the last bit. I've kind of given, all the physics is done. So I'll give you all 5 more seconds. Pick something if you don't have something. 3, 2, 1. All right, let's solve this out, y'all. So we're just going to take this equation. This one right here. So MGH initial equals MGH final plus MGH final. All the masses cancel. All the gravities cancel. H initial equals 2H final. You plug in the numbers. H final equals 5.
Wait, how is the initial potential energy
From this equation.
Yeah. Where did you get that equation?
From this equation.
Oh, so you just like.
Kinetic energy initial went away. We swapped out KE final with U final because that was one of our givens.
Oh,
Yeah.
Oh.
So it's a fun little puzzle. It's a fun little like.
it's not like a system of equations.
Yeah, I mean there's some if this and so anyway. There you go. Oh, do I want to be mean?
Because you're not setting.
I kind of want to be mean.
Or like,
All right, and I gotta actually calculate it to make sure I get the right answer. But I'm gonna give you all same exact problem. It's not mean because most of the work is there. It's not too mean. If an object is dropped from a height of 10 meters, at what point is the final kinetic energy? When the final, all right, I'm going to reword this. When the final kinetic energy equals the potential energy, how fast am I going? All right, and I got to do some quick math to make certain I don't just put, I'm fairly confident one of the answers is one of the ones previously, but fairly confident is he confident enough to put it? Always double check your work.
wait, how fast you are going to set the object?
Yeah, the question is how
Just
fast
swap out.
how fast is the object going? So I got to do some math here,
So,
which means you probably should do some math. Yeah, good thing I checked. It is not one of those answers.
yeah.
Yeah, I didn't write it out because I didn't. Yeah, I'm pretty confident in this. All right, is the answer 98 meters per second? Is the answer 2.5 meters per second? Is the answer all right, there you go, y'all. The same problem. A lot of the setup is going to be identical. But now I'm solving for something different. So there's many ways you all can do this. You can actually use the answer from the last problem to do this problem. Oh, does it? Oh, yeah, fun fact. Well, you'd have to know when it happened. You'd have to know it's 5 meters. So, do similar work. See, this is kind of a test. Did what I just did make any sense to you? Do the same setup, y'all. Like steps 1, 2, and 3 are almost identical. Yeah, that works. We use the final sentence.
Like the one happened where
That's the way I'll end up. How we doing, y'all? Alright, so let's think through the logic of the last one. Yeah, so we look at this. What's my so final kinetic energy we don't know. Initial kinetic energy. What do we know about it? Go through it. And then the thing that's cool is we have a relationship. KE final equals so like you either turn this into a or you turn this in this case, though, just see what happens. See what happens. You know that swap that you left in the KF. And see what happens. And this specific problem says when the final equals final. Alternatively, I could have said, hey, when the final equals half the potential. And then I think it's a relationship. KES equals 1/2. And then I would use that substitution. Yeah, that's the idea here. We just we're setting up relationships and then we're putting them into each other. Alright. Oh, that's yeah. How are we doing over here, y'all? Yeah, that works. That's not necessarily. We're not actually working on
That's very interesting.
Yep, so check that right there. And then we just look at this and we use some of the information we have. Kinetic energy final, that's where I'm trying to figure out. Kinetic energy final, also figure out. Kinetic energy initial, what is kinetic energy initial? It's going to be 0. This term's going to be
Really
KF yeah, so you can either
like that
or KF and we have like a separate equation. All right, y'all. So just to kind of show you all what's going on here, same stuff as before. Conservation of energy. So potential, we got kinetic energy initial plus potential initial equals kinetic energy final plus potential final. All right, we have this. And, let's simplify this a bit. Whenever you all do conservation of energy, we generally immediately just kind of knock out the ones we don't care about. Case in point, kinetic energy initial 0. Great. So potential energy initial equals kinetic energy final plus potential energy final. All right. We know everything we need for this. MGH, we got that. MGH initial, we got that. But on this side, we got 2 unknowns. But there's another equation we know. When the final equals the kinetic. This relationship I'm about to write is only true for this problem. This relationship is only true for this problem. Do not use this relationship in future problems. This is only true because of this statement. When the final kinetic energy equals the final potential energy. I just wrote that in math terms. That is only true in this problem. All right, why is this useful? What are we solving for in this problem? Final velocity. So which energy do we care about? Kinetic or potential? Kinetic. So swap the. So what can we do with these 2 equations? We can swap that UF. It's a system of equations, y'all. Gosh, how many highlighter colors can I do here? This is this. Swap it. Swap it. Great, and then you just do math. So this problem is really an exercise in playing with the equations. Playing with a system of equations, realizing you can substitute things in. You know, and let's make this a little simpler. You know, if you have 2 KEF plus KEF equals 2 KEF. And then you just do math. And I will close this out in 5, 4, 3, 2, 1. If you all do the math, you find that the answer is this. Look at that. Good job. All right. The purpose of this equation is just playing around with conservation of energy without having a bunch of numbers. The vast majority of problems, you're all going to have a bunch of numbers. Numbers generally make a problem easier. This sees if you understand how to actually the logic. It kind of gets you out of that just like brute force solving things. All right. Okay. There is 2 types of kinetic energy. There's 2 types of conservation of energy problems. There's a type where you don't lose any energy. No energy is lost to the system. The system like maintains all its energy. In that case, no work is done because work is energy added or taken away from the system. Great. If work is done, there is a work due to friction. And you have a choice. Notice, I put this work of friction here. I put it as a positive. If you want, does friction add energy to a system or take away energy? It takes away energy. It may be hard to see that here, but if we just rearrange this equation, y'all, we're going to see that UI plus KI equals UF plus KF minus. If you prefer, this is the exact same equation. And this shows I lost energy due to friction. Okay? They're both the same equation. The second one I think is actually more clear because it shows that you lost energy. But the idea here, work, you generally either kind of put on the left or right, and to that end, there you go. Okay? Now, when you're plugging this in, you are going to still do the angle stuff. You're going to find that's going to be a negative. It's going to result in, if I start with 10 joules, I'll find that friction took away 2 joules, and I end up with 8 joules. When you all do, that's why work's on the left side. Even though it's on the left side, it'll end up being a negative value, causing you to lose energy. All right? So, honestly, that's actually why this first one is kind of better. Anyway, let's do some things, y'all. Okay, how do you solve these problems? Is it even a conservation of energy problem? If there's a beginning and an end, then conservation of energy is a possibility. If I say I start somewhere and I end somewhere, conservation of energy is a possibility. Can you account for all the energies? Can you account for the kinetic, the potential, the friction, whatever, all those things? If so, great, you can do it. You all will find that all the kinematics problems, all those projectile motion problems we did, you could actually do with conservation of energy. Anything with height and velocity, you can generally do conservation of energy. It's great. All right, no friction, no work due to friction. Yes, friction, yes, work due to friction. All right, and at this point, we're just going to practice problems. Okay, do I want to do this one? Yeah, sure. Okay, and the picture to the right, what type of energy does the ball start with? I got a beginning and an end. Beginning's on the left, it's when it's compressed. End is on the right.
Oh.
What kind of energy do I start with? We have to do the next problem. We're actually going to use this. No. The ball starts compressed, gets released, flies up into the air. What type of energy does it start with? Start is on the left, y'all. Start is on the left. This one. In general, well, left to right. Left is beginning, right is end. That's a rule of thumb you can generally follow. When you draw pictures, I recommend doing the same drawing. Left to right, left to beginning. All right. Give y'all 5 more seconds. Don't overthink it. In 5, 4, 3, 2, 1. All right. I'm going to be very kind. So the answer, we'll close this. There is one answer for sure, one answer you can make an argument for. All right, a spring is compressed. It's elastic potential. Like that's, definitely there's energy stored in a spring. I don't care how you look at this problem. If a spring is compressed, it's got energy stored in it. That's like, I don't care if you're in space. I don't care if you're on Earth. I don't care how much it's compressed. Doesn't matter. If a spring is compressed, you got this type of energy. You can make an argument that it starts with gravitational potential energy. You can make an argument that it has this energy as well. You could say, I start above ground, so I start with some potential energy. That's fine. But this is where I'm going to encourage you all. Set your starting height as 0. Why is that beneficial? Otherwise, you got to do extra math. You get to decide where 0 is. If we decide that we start at 0, what's the benefit of that? The benefit of that is that potential energy in the beginning is 0, and we don't have to put it in the equation. So, you get to decide where 0 is. If you decide to put 0 down here, you run into a bit of a problem. Your life is harder because you got to decide how much it's above that. And you don't know that, and you can still solve the problem, but it's going to hurt your brain a lot more. So anyhow, I will give the points to both these because technically you could argue it's above ground. But this is where I told you all, for convenience, you get to decide where 0 is. Put 0 somewhere where it makes your math easier. All right, great. All right, same question, but at the end. What type of energy does the ball end with? This is how you do these problems. What do I start with? What do I end with? At the highest point, we're going to say it reaches the highest point. That's a very key word, the highest point. Oh, I should have taken a break. All right. And after this, we'll take a break. I'll put the next problem up, and we'll take a break kind of thing. All we're doing the rest of class is solving these 3 problems. We'll finish early. This problem's pretty easy. It's a classic conservation energy. All right. Close it out in 5, 4, 3, 2, 1. All right. So what energy do I end with? Is my spring compressed anymore? No, nothing is squishing my spring anymore. There's no energy stored in that spring. And we're asking about the energy that the ball has. The ball is not compressed in the spring. It's getting jack squat from that spring. So it's not that. Is it above ground? Yep. Remember we decided to define this as 0? I guess you can make the argument, you can decide to make where it ends as 0. Which is fine. Kinetic energy, it stopped moving. No kinetic energy. Thermal energy, I hope no one put that one. Thank goodness. All right, you could make the argument that it has thermal energy, but did it get hotter or colder? No, so we're not going to care about it, y'all. In general, y'all, we're not worried about thermal energy in this class, because how the heck, you can't calculate that easily. If you all take some thermal and statistical physics class, you can calculate that. All right. Feel free to start this or feel free to take a break, y'all. We got 3 problems to do. I'm not gonna start doing anything for the next 5 minutes, 7 minutes, whatever. So take a brain break if you want. When we get back, we'll kind of start this problem and then do the other 2, and we'll probably finish it. We will finish it. And then Tuesday we'll start momentum and do a lap on energy. Rest your brain, y'all. Let's see, was I kind? Okay, so this problem I got from OpenStax, and they actually made a tiny error, but it doesn't matter that much. The subtlety to this problem is its final height is not 5. Its final height is 5 plus d, which is really, really subtle. It doesn't actually change the answer much because it doesn't get compressed that much. But I will talk about it because it's just where did you set y 0? You did not set y. You didn't set where it extends at 0. So that's just an interesting thing to think about, though. It can matter a lot depending on the problem. Yeah. Oh yeah, the newtons per centimeter. They're not going to. Yeah. And that's where I hope. Yeah. It's good. Stuff like that's good because sometimes they are given that way. Let's see, I forget what the other problems I've given are. Yep, good. These are good problems. Yeah, conservation energy is fun. You can do a lot of cool stuff with it.
I like conservation. I like conservation.
Yeah, it's so useful.
Yeah, in my astronomy class, when we did like orbital stuff, we saw
it was all cut. Yeah, so after momentum, we will do universal gravity, and we will find we will then derive that using the work equation and get the energy, universal energy. And we'll use that to find escape velocity.
Yeah.
We'll do a problem on that.
Because we did escape velocity, and we'd also just do things like if you're in an orbit, if like your sun is here, if you're in an orbit here, how much energy do you need to put in to reach a circle orbit here, or to reach a height here? Yeah. If you're like in an orbit here.
Oh, to increase your orbital radius? Yeah,
to increase your I guess it's helium if you're at the sun. But it's just if both of your you just take
well, it should just be a conservation. I mean, I guess you're going
because
faster though.
It's over R because you go slower.
You go slower.
So it'll balance out with your increase in radius and your decrease in velocity at your final.
So does it end up so you go slower, so your energy stays the same?
Yeah, your energy stays the same because you are
farther away.
You're farther away.
Does it work out that? I was like, I don't know.
Yeah, because you get like because it's just you initial plus the final equals final plus
so you gotta put the T and the over R, but then you gotta do centrifugal to figure out your velocity.
Your velocity is pure tangential.
Yeah, so you're gonna have to use centrifugal.
Yeah.
Velocity equation. Yeah.
And
you're gonna relate that to the acceleration, which would be G over R squared.
Yeah.
Yeah, I'd have to work it. That's interesting. I've never worked out that problem.
Yeah, we did a whole homework problem that was like, it was given more. It was like starting on the surface of Mars. How much energy do you need to burn against gravitation to reach the Earth's orbit?
I wonder what counts as Earth's orbit.
It's just the radius of the Earth
Oh, okay.
to be captured by Earth's gravity.
Okay, because I
Yeah, 1 inch.
because actually I don't know. Yeah, if you escape Mars, at what point do you define it?
Because it's you
So
have
say
sun
you
here.
say you escape Mars.
This is Earth.
I've never done a problem with go from orbiting one planet to orbiting another planet. I don't know at what point the tipping is it just when the force of the gravity due to Earth is stronger than the force of Mars is the tipping point at which point you
It's
say you're orbiting.
Yeah, the force of the sun. Because
That's a technically orbital.
it's two problems. It's
That's
Which
what
is
the
really-
moon is
Our moon
doing.
a great example.
yeah,
Oh, because the
There you
sun.
yeah, it's two problems because it's like how much velocity do you need to escape Mars's hill radius? Because then you're in orbit around the sun, and then you do a conservation of energy to get here. And it's not asking to circularize; it's just to get here.
And my best understanding with gravity,
Yeah, it was really fun. I really
so
liked it.
my best so gravity assist. I've heard those, and I was always like, my best understanding. Well, I was just thinking about it recently. My best understanding with that is a gravity assist because the plane's moving forward. It kind of tugs you.
Yeah, you steal a little bit of energy.
Yeah.
It tugs you. Yeah, so you have to be to get the gravity assist. I assume you have to be like going in line with the direction that's moving.
Yeah.
And when you slingshot around, you got to somehow slingshot in a way that you're not then getting tugged backwards to cancel it. So I don't know exactly how that. Where do you want to get slingshot?
It's surprisingly.
I guess you get slingshot just the other. You wouldn't want to swing all the way around the planet. You just want to swing like halfway around it. I'm
It
assuming
like depends on what direction.
Yeah,
because you wind up on the other side, so that way it's not tugging you. You gain the motion of the planet, and you don't lose it from swinging back the other
Yeah,
side.
if you're coming in like this way, if you want to get slingshot, then you basically come in like this.
Yeah,
And
yeah.
You
Go the other side. Yep.
You get velocity.
Which is cool.
There's an online calculator.
Oh, and Kerbal Space
Nice.
Program.
Yeah.
Oh, funny. All right. So we'll go ahead and resume. You might have already started this problem.
Yeah, there's
If you haven't, the picture's already drawn, but write down your givens. Be careful, y'all. There's some unit conversions in here. There should be some units in here that are like trigger units for you that realize, oh crap, I gotta convert that. Do that ASAP. Do that when you write your givens, otherwise you will forget. So, write your givens. Write what you're missing. If you ever see a problem with a spring, it is almost a guarantee to be conservation of energy. If you see a problem with a spring and something moving or going at a certain height, almost guarantee you it's a conservation of energy problem. For the spring gun. Yeah. You notice that the spring is massless. If it was not massless, it would have its own energy after oscillating, and that would be a pain. So we ignore that. So we're caring about the thing that gets launched. So write down your givens. Write down what you're solving for. Decide what types of energies you start with and end with. All those things. And in a little bit, I'm going to point out something to you all that I can almost guarantee a lot of people are going to miss. Because it's very subtle, and it doesn't change the answer much, but it is important to point out. So we'll see in a second. It really has to do with writing your givens. I will be able to determine in step one whether or not you missed something important. And I'll put the final answer up here. I might have to work it out, because I don't know if the final answer I put online is... How gross does this turn into? Yeah, if you do this problem correctly, it's a quadratic formula.
I just use conservation. I seriously just use conservation. Oh my god.
So then something coming up. There's no way around it. So if you set up this problem correctly, you have to do a quadratic formula to get the precise answer. I'm gonna give you all a few more moments to write down your givens, and then that's gonna determine whether that's the part that's gonna determine whether or not you realize it's the conversion. So here's the logic items. 1 centimeter is, so that will also work. That will totally work. 2 centimeters will cancel. Yeah, the logic here is spring constant is how stiff it is. How many newtons you need to push it 1 centimeter. That's the logic to this spring constant. So if I need 12 newtons to push it this far, am I going to need more or less to push it? So that's how I actually do it. I don't actually ever set up the dimensional analysis. Great, like that works perfect. I think through, okay, if I need that much to push it 1 centimeter, do I need more than that or less than that?
Oh, okay.
And I know more, so okay, I'm gonna multiply by 100, not divide by. That's how I check my work. The logic should make sense.
Yeah, I did it a different way.
And you,
I assumed I got the correct answer.
I think you have to do the quadratic. I don't think there's a way to do it without quadratic.
I mean, I use contribution of energy and the split into two systems.
Yeah, so the challenge there is the final height is an h. H plus x.
Yeah.
So that turns into it. It should turn into a quadratic.
But I can
Oh. Oh no, you did the first little tiny bit,
yeah,
and you found out how fast it was going?
Yeah. If I would MGH from that.
Does that work?
I think it's the same answer.
It might. Alright, let's write down our givens, y'all. You tell me what's given. Holler it out. I believe in y'all. What givens did y'all get? Final height. What is my final height? It's not 5. Yeah, so where is my 0 located? We're going to define, so we're going to say y initial is 0 here. So if you all look at this picture, that's my y final. It's really subtle, and it honestly won't change your answer that much because the final answer, the spring doesn't get compressed that much. It's a really stiff spring. You don't need that much to make it go this high. But I purposely am talking about this problem because OpenStax actually didn't do this when they solved their problem. Their answer did not account for this, but I think it's really good to account for it because it could matter. This could matter if the spring wasn't this stiff. If this spring constant was way less, this would actually make a big difference. You have to account for the spring compression because that's the initial height is where it starts. Final height here is not 5. You can see it in this picture. Y final is 5 plus delta, however much it gets compressed. Anywho, so we'll jot this down and then I'll do attendance. So y initial equals 0. Y final is not actually completely known. 5 plus d, however much is compressed. All right, what else is given?
Oh, attendance.
Yeah, at some point. What else is given? Mass. What's the mass? 0.015 kilograms. Is that? Yeah, that's good. All right, what else is given? All right. Am I good with leaving it like this? No. Now, the question always gets with these ones, this always throws people off. I got to go from centimeters to meters. Do I divide by 100 or multiply? And there's 2 ways you all can do this. 2 ways you can do this. You can just do it like mathematically. You can do 12 newtons per centimeter. And I know I need to cancel out those centimeters. How many centimeters are in a meter? And great, you can do it that way. But honestly, that makes my brain work more than I want it to. What I do, I know I'm going to divide or multiply. This unit says every centimeter, it needs 12 newtons of force. Every centimeter. So if I push it a full meter, do I need more or less? More. So I multiply. That's the logic I do. You do whatever works best for you. All right. We are solving for, in this case, we're going to use the variable d. If you want, you can call it delta x or whatever. In the picture, it's d. Do you all, whatever. Up to you. And then you do some math. This is where I warned you all. If you set this up correctly, you have to do a quadratic formula. And while you're having fun doing the quadratic formula, let's have... That's what I slowly drink mine throughout the class as well. It's something, that's why I've started keeping tea in my office, because it gives me something to drink, like sip on as I'm working on things that won't get me like buzzed and jittery. Yeah, so Connor, what did you do now? Because I'm still not.
I assume I got the right. I don't know.
I don't know the right answer either because I haven't done the quadratic formula. I don't want to. What did you do?
Two products.
Sure.
Yeah. Two systems.
Okay.
So.
Yeah, right at your, because the logic I'll be able to check without needing to check that. For Leo or for me? When we consider it fully compressed, yeah, think of like a spring fully compressed, it's not moving. So we only have pinch on it. We only have spring moving in the beginning, and at the end we only have. No. No air resistance to this problem would be impossible to calculate. Like, you could not calculate it with air resistance. You would have to know. Right. And I will get the answer because I don't remember what it is. And I will do the disgusting quadratic formula. Sure. So this is going to be conservation energy. What energy do we start with? Yep. So do I have any other types of energy? So in the beginning, do I have any other type? Nope. So 1/2 kx initial squared equals whatever energy I invest. What energy do I invest? So conservation, whatever I start with is what I invert. That's how we set up these problems. Anything else? Any kinetic? Any spring? Nope. So you just set those two equal to each other and solve. Yep. All right, I'm going to close this out if you need it. Leo. All right, y'all. The key to this problem is just this equation. Energy initial equals energy final. And we already answered clicker questions. What energy do I start with? Spring energy. What energy do I end with? Potential energy. You set them equal to each other, and then you have the pleasure of doing a quadratic formula and getting an answer that I haven't plugged out yet. We'll see what it is. So yeah, what energy do I start with? You have to, so think through that. What energy do I end with? Again, they were the last two. What energy do I start with? Elastic. What energy do I end with? Gravitational. Whatever I start with is whatever I end with. Do the math. I will do it as well to get the quadratic, or Angelina's doing it for me.
Just to clarify, so when it's at 5 meters, it's about no velocity, it's the highest.
Yeah. At 5 meters is at its highest point. Let me, that's shot to a max height above the spring equilibrium position. Yeah, so mainly the mistake that OpenStack's made is their picture did not match their logic or their wording. Yeah, what's H going to be? Yep. Yep, just replace H with 5 plus X. Then you solve. Yep. That's the cool thing. You're building the equation. Conservation of energy is all about building the equation that you're ultimately going to solve. Every time you do a problem, it'll be a slightly different conservation. You'll start with different energies, you'll end with different energies. And so you build the equation, then you solve. But it all just boils down to what do I start with, what do I end with? Alright, how are we doing now? What do we start with? What kind of energy? What kind? Gravity or spring? Yep. Yep. What's the equation for that? 1 mvx squared. Do I have any other energies to start with? I don't know. So this side just equals 1 mvx squared. And then equals, and then use what energy do I end with? What's the equation for that? There you go. And then you just plug in the things. All right, so just to kind of write out this, so the only options we really have in this course are as following. You got spring. So this is kind of the checklist you go through. All right, this is the only 3 types of energy I've really introduced to you all. I guess there's technically work due to friction. In the beginning, do I have spring energy? Yes. In the beginning, do I have gravitational energy? No. Do I have kinetic energy in the beginning? No. Do I have spring energy at the end? No. Do I have gravitational energy at the end? Yes. Do I have kinetic energy at the end? No. This is the checklist you're going through your head. What energies are present? So long story short, we get that the spring energy in the beginning equals the gravitational energy at the end. And then you just need to look through your notes. What's the equation for the spring energy? What's the equation for the gravitational energy? Plug them in. Do the quadratic formula. Does it work?
Yeah. Nope. I mean, it involves square root.
So you got X. So H is at 5.
No, H is 5. It's still right. It's 2 parts. That's how I
Did it? What if it be squared? This.
like all
Yeah, so the problem here is you end up with the same thing that we end up with, but your H isn't equivalent to an R. Where do you define 0x? So here's the problem in the beginning then. If that's 0, you start below.
I mean,
You have
at that point,
so you have
it's just a difference of
so you do end up with you still do end up with like you have to do quadratic still.
if
You have to include that in there. Yeah, it's very tiny. It's very, very tiny. So all right, so what should the answer be? All right, who got the answer? I still haven't had the time to do the quadratic. What'd you get? 0.0351. All right. It is super tiny, but it's worthwhile. All right, so this is the answer you all should get. If you do not consider the spring getting compressed, if you don't consider that plus, so let's just jump over to this. Put this here. All right, so step 4. So what does the energy actually end up being? So in step 4, you find that 1/2 kx squared equals mg h plus x. You know what? Let's just put it, whatever. Just to leave it, I don't care if you leave it as d or you put it as x, it doesn't matter. So this is what it ends up being. When you end up doing this, so it becomes a quadratic formula. When you solve this, the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. There is no avoiding this quadratic, y'all. There is no avoiding this quadratic if we set up this problem this way. You end up getting that x equals 0.0351. If you do not consider this, so this is correct. If you do not consider it, you get 0.035, which is not much different. It's not much different, but that's because the spring is really stiff. If I made the spring not as stiff, this answer would be way different. And the reason that I emphasize, the reason why we are doing this is because the compression, like, you have to be careful. You have to be careful when you draw. That's why drawing your picture is useful. We have the picture here. What you're doing needs to match that. And so, anyway, it's just, that's why I like this problem. It's a tiny bit more complex than it seems at face value. You have to consider that little bit of compression. It matters. Like, it can, depending on the problem, it can matter a lot. And if you don't consider it, then you're not going to get the right answer. That's just the reality. All right. Feel free. If you have any questions, we'll kind of go around and answer it. But otherwise, another one. It's all the same thing. What energy do I start with? What energy do I end with? All of conservation of energy. All these problems, that's all you're doing. Once you do a couple of these, they're really simple problems once you get that in your mind.
Oh, okay. So it's just like a and then I this and stuff like this.
Okay.
So I
Okay, so what are you calculating? I'm not sure. Yeah, plug it in. Let me grab a calculator. So we got 600. That's good. 0.015 times 9.8 equals 0.147. What is the spot? Oh, that's fine. Yeah, 5 times 0.015. So negative b, so negative plus or minus. So like, I guess you have to decide whether plus or minus. We're gonna go with. We're gonna probably go with plus. Should we do minus? Should we do negative? Yeah, which doesn't make sense. B squared. Negative b plus or minus for minus 4 times 600 negative. Divided by 2 times 600.
Because I just rotating here. It's like so much. I don't know if that's as simple as doing the dropping guy. Keep playing.
Yeah, I do get the negative 0.035 volt. Negative 8. Negative entry. Like this is the right answer. So why is it negative? My logic here is just use the 2 off.
Because that could be fine because this is 0.340.
And my logic is I know I need to use more than if it's compression should be more than if I didn't count for that. Because I need to, we're having to go higher point. So that's why if the other answer is 0.025, this is the right one.
Because
I'm not quite sure why.
I just
All right.
I just didn't use it wrong. So I don't know if tension is just teaching.
So what's cool, y'all? We don't care that this is going in a circle. Who cares if this is going in a circle? Doesn't matter. Conservation of energy doesn't care what path you take. So great, I got a ball at the end of a string. So at the lowest point, it's down here. And it's moving with a speed of 10 meters per second. So we always draw a picture, y'all. Draw a picture because it helps. That's my beginning. It's moving at the bottom. At the end, so great, it's moving there. And my question is, how fast is it moving? So this is initial, and this is final. At the highest point, how fast is it going? It is moving. We don't care that it's going in a circle. We don't care about the direction of velocity. You don't care about any of those things when solving this problem. All you care about, so this is 2 meters here. All you care about is what's in the beginning and what's in the end, and no vectors. It's a scalar problem. Energy is a scalar. So, to that end, you can kind of ask yourself this question. Where do you all want to define 0 as? Where do you all want to define 0 height as? You can? You can define 0 height as here. That's an option. At which point its initial height is -2 and its final height is +2. That's valid. I generally recommend make your 0 somewhere that cancels out some math for you. This is valid. What we just wrote here totally works. Or we can start it at 0. The benefit of that is it's one less thing you got to plug in a calculator. So I'm going to define the bottom as 0, but I really don't care where you all define it as long as you're consistent. All right, great. So let's just say my y initial is 0. You all tell me what else is given. The mass. Sure. What else?
Yes, the whole system.
We know G. What else? The y final based on, and this is going to be based on where you define 0 at. What's the y final? It's this, y'all, from the beginning to the end. Or it's from 0 to however high you are. Yeah, so what's y final? 4 meters. This is the benefit of a picture, y'all. A picture lets you see all of this. Without the picture, you got to kind of hold this all in your head, and it hurts. If you draw a picture, we can clearly see. If I drew this picture well, it starts 2 meters down here, and then it goes 2 meters above that. And this is the rule of thumb, y'all. If you do not understand, if you can't visualize the problem, it's almost a guarantee you're going to have a hard time solving it. If you don't know what's actually physically happening, yeah, it's a nightmare to solve. At that point, you're just relying on math, and it's very likely the math you do might be wrong. Put the wrong number here or there. All right, what else? What else is given? Initial velocity.
Correct.
All right, cool. What are we solving for, y'all? Eventually, we'll find tension force. When we do tension force, y'all, I'm going to warn you, that's just going to be a kinematics problem. Not kinematics. That's going to be a force problem. Yeah, part B actually has nothing to... we only use part A is what we just learned. Part B is something I could have asked you on the last test if I'd given you the velocity. Part B is something I could have given you all last test. I could have said an object's moving this fast at the top. What's the tension in the string? Tension in the string. All right, and we'll do that. It's good to remind you all how to do those problems. The final is cumulative, so we don't want that to leave our brain. All right, we're finding final velocity. Step 3, conservation of energy, y'all. Energy initial equals energy final. What energy do I have at the beginning? What energy do I have at the end? Set them equal to each other and do math. All right, and I'm going to go around and assist you all in building that equation. That you have to ask yourself that question. What type do I start with? What type do I end with? Boom. Yeah, I didn't touch that.
Oh, because it doesn't work.
That's valid. Yep. Yeah, that's a great question. If you all set the midpoint as 0, you would start at -2. You can have a negative potential energy. You can totally have a negative potential energy. A negative potential energy just means it's a small number. It's less than 0. Like, that's square. Yeah. The string swings in a vertical plane. Oh, that's valid. I mean, at that point, you don't know its final height is the problem.
Yeah.
And you can't solve it, I think.
Well, the final height, because you're given the velocity, you can.
Oh. No, that's actually a very good point.
Yeah.
All right, my bad, y'all. The question is, we actually don't know if it made it this high. I lied to y'all. I'm so sorry.
Because he finally knows because whatever this is all those.
Yeah, okay. I will warn you all, there's actually, there's 2 potential solutions to this, depending on, and you actually, I guess, don't know which one's valid until you do both, I think. So this only, the one I gave you all, I'm assuming it reached the highest point.
Yeah.
I don't actually know if it does. We're going to find out. Y'all are going to find out in the math if it actually reaches this point. If it fails, we'll do the other way.
So we don't know why final. It's not. It could.
Yeah, it could either, and this is a good point. If this thing makes it to the highest point, this is how we set up the problem. If, instead, let's actually draw this. I assumed something very important here that may not be true, but we'll find it in the math. If what I told you all is not correct, you're going to get something you can't calculate. You're going to get square root of a negative number, I believe. Anyway, so I assumed the thing made it all the way to the top. That's one possible solution. Another possible thing is that the thing starts down here, and it only makes it some arbitrary height up, but it doesn't make it all the way. In that case, if that thing swings all the way up there, what's its final velocity? 0. So actually, in the problem I gave you all, if your problem doesn't work, the final velocity is 0.
Wait, there's another.
Because that means it's going to stop.
There's a possibility that if it makes it over, if it has a
Okay,
velocity at the top too.
this is fine then. Yeah.
Okay.
Yeah. This is either it just makes it or makes it past it.
Okay.
Yeah. So if it doesn't make it, the answer is really obvious. If the object doesn't make it, if I toss something upwards and it just goes whoop, it stops at the top. You'll actually figure that out in the way we set it up. If the answer doesn't work, then the answer is 0. Because that means it didn't make it. And that means the final velocity is 0. But if this problem doesn't make it. That's fairly complicated.
I think it has a velocity at the top. I think it's going fast enough to where it still has that velocity. Because this is greater than 4. Which is comparing bottom to whatever it is. Which should not be possible.
So we don't care about in that case, it'll know.
So I think it.
It's gonna end up with some
So we can never go higher than 4.
Because it thinks it's going higher than it can. So how do you do it? Because then it would have.
All right.
Yeah, because you do have that final. Because if you look at the height, this is the height where it's supposed to be. This is greater than 4. So it has a final velocity at the top.
That's good. I just assumed it did.
Yeah.
I'll clarify that in the problem moving forward, but I guess you'd find it. All right. How you all doing over here? Did you figure out what energies it started with and ended with? So in the beginning, we're at the bottom. Yeah, is it moving?
Well, V squared.
I can pull it up. I don't have it off the top of my head. I can find it real quick. It should be. What is the speed at the top of its path? 0.5 times 1. 0.5 times 10 squared minus 4 times 9.8. Here. I can also pull it up. I'm going to double check myself. I got 3.28.
I skipped steps.
All right, which one are we working on? I messed up something. I'll have to write it out and double check it. There you go. Yeah, so I flubbed something in my math. You get it?
No, he was just like, I'm gonna make an educated.
All right. So what energy is it start? So it's moving in the beginning. So we have kinetic energy. Does it have potential energy? Not due to gravity, not due to spring. Great. So, all right, y'all. So what energy does it start with? Only gravity. Not gravity. Only kinetic. That's the only type of energy it starts with. At the highest point, is it moving? We're going to assume it's moving, otherwise the answer is trivial and it's 0. Either the answer is it's moving and we have to calculate it, or the answer is it's not moving and the answer is 0. We can assume it's moving, and if it's not, the math will actually not work. It won't be possible. You'll get the square root of a negative number, which is imaginary, which says, nope, you can't do that. You can't make it that high. So it is moving. Does it have gravitational potential energy at the highest point? Yep. Ta-da! Does it have spring energy? No. Is there energy lost to friction? No. Plug in the equations. Plug in the things. You build the equations, y'all. Build the equations. What do I start with? Set it equal. What do I end with? That's every single conservation of energy problem. If there's work due to friction, that goes on the left side, because it takes away the energy from the system. All right. And then part B is a good challenge. If y'all got through part A, easy peasy. Part B is a good test. Part B is a question. A, something's going 4.6 meters per second at the top of the circle. What's the tension? I could have asked that in the last test. It's not a energy problem, it's a force problem. And circular motion. You got to calculate the centripetal force. You're going to set that equal to the draw a free body diagram. Sure. So, can I give you initially just negative? How's that? So then what's the equation for the next? All we're doing is we're just putting the equation equals. What's the equation for today? Plus, what's the equation? There you go. Plug in the numbers and solve. Yeah, that's it. All right, how y'all doing?
Oh, I got it.
Nice. Alright, let's see. Yes. It's 4, because if you look at the picture, if we define it starting as 0, y final is all the way from here all the way up to here, which we can see is the 2 plus the other 2. Yeah. I flubbed something in mine, so I forgot to multiply by 2. All right. So this first, just you all are going to end up memorizing the equations for kinetic energy if you haven't already. You're going to use these things so much. So you just plug them on in, do the stuff. All right. For part B, y'all, again, part B is just a review of stuff from test 1. Part B is a review of stuff from test 1. We are asking for the tension in a string. Guess what we got to draw? A free body diagram. So we're going to start fresh. I say start fresh. We're going to use some things. So at the top, what forces are acting on it? Gravity. Which way is that? Down. What else is acting on it at the highest point? There's my picture of it. What else is pulling it / pushing it? So there is so centripetal force will be the sum of all forces acting toward the center. We will use that. What other physical force? So like gravity is a physical force. Tension. Which way is tension pulling, y'all? Down. And then your classmate raised a good point, and I drew it in my picture. It's going in a circle. So if something is going in a circle, reminder to y'all that centripetal force equals, or let's write this another way, MAC equals the sum of forces towards the center. Centripetal force equals the sum of forces towards the center. If I'm going towards the center, is it positive or negative? Positive. So I have MAC equals tension, positive or negative? Is it going towards the center or away from the center? Towards, it's positive. Gravity, towards the center or away from the center? Towards. And you may be like, all right, great. How do I solve this? We're solving for tension. We know FG. Acceleration, is there a handy equation that might help us given what we know? What is that equation?
Oh, wait.
That's the definition of centripetal. That's an equation that relates centripetal acceleration to how fast you're going. You all know how fast you're going. You just found it in part A. You all just found out how fast you're going in part A. Try it out. You got everything you need here.
So at the top it makes sense.
So on the bottom, gravity is down. That's toward the center or away from the center?
You should plug in the velocity that they got.
So if we draw a picture of it, so at the top,
Are they asking for tension at both?
the way we towards the center is positive. At the bottom, tension upward, gravity is downward. And so our rule is when you're pointed away from the center, put it. So instead plus 2 negative FC plus T equals mv squared over r multiplication of velocity. It's combining a few things together. So yeah, this is a fun problem, y'all. I say fun. This problem combines like everything I've taught you except for kinematics, which is cool. I don't know. I think it's cool to use a bunch of things. Oh yeah, the answer is 58.8 and 0.78. Are those wrong?
Yeah.
No! Oh my gosh. Okay, sorry. If they're wrong, it's OpenStax. Yeah. That's I'm blaming OpenStax. But I can subsequently, I suppose, blame me. All right, let's solve it, y'all. So for part B at the top, we have mv squared over r equals tension plus m times g. So tension is going to equal mg minus mv squared over r, which is going to equal 1 kilogram times positive 9.8 minus 1 kilogram times 4.6 squared divided by 2. Oh yeah, that's nowhere close to that answer. Where do they get their answer from? That's bad. Sorry, y'all. I lied to you. Why is it negative? That's kind of weird. Did I move it the wrong way? Oh my goodness, that's why it's negative. mv squared over r minus mg. So you get 1 times 4.6 squared over 2 minus 1 times 9.8. So you get the same answer, but hey, well, that's not one of the answers. It's just in the wrong spot. No, that's fine.
That's the right spot.
Yeah.
You
Yeah.
started with the top.
Yeah. Okay, we're good. We're good. Tension at top.
Yeah.
Great. I started with the wrong one. Whatever. So that's at the top. To the power of. So is all well then?
At the bottom, it's supposed to be 59.8.
So we move that to that side. At the bottom. All right. We need a new free body diagram, y'all. At the bottom, things change. Which way does gravity point at the bottom? Down. Which way does tension point? Why does this matter? We do the exact same equation. mv squared over r equals tension, positive or negative, towards the center or away from the center? Positive, it's towards the center. Gravity, towards the center or away from the center? Away. Same exact equation, but it's slightly different. And the velocities are different. So you do you rearrange it. T equals mv squared over r plus mg. Make certain you all do not put 4.6 here. V bot. V top. At the bottom, I think it was 10 meters per second. Yeah. Plus. So is there a typo?
I think it's 59.8, but on the computer said 58.8.
10 squared divided by 2 plus 9.8. 59.8. And the answer here says 58. Oh my goodness.
This is a one type.
No, that stinks. It is very slightly wrong.
You're off by 1 and fine.
Yeah. It's within 10%. It's not within 10%. It's not within 1 to 2%. I guess 2%. Technically, it is just barely within 2%. So yeah, I'll let y'all have any questions, but this is basically a review of forces in circular motion. No, I guess it is. That whole velocity, that's the correct velocity. You're fine. Your logic's good. All right, y'all. Again, this problem is not gonna like this would not show up on the next test, but it is something I could put on the final. Something swinging this fast. What's the tension force at the highest point? It's not a super complex problem mathematically, like solving it, but you have to. Can you set this up? Can you set this up as something you need to know? All right, y'all. Here's the last problem. Last one, last variation. Now we got air resistance involved. Draw a picture. Write down your givens. Write down what you're solving for. And in this case, there is air resistance. And so I will remind you all. I'll even jump to step 3 and remind you all. If there is air resistance, you do the energy initial plus the work of friction equals energy final. If there is air resistance, the work due to friction goes on the left. You do need to do the, be careful with that cosine of the angle, y'all. You have to consider that. Okay, actually, no, this one says find it. Let's see. Do you all have to break this into 2 Nope. Nope, don't have to even break this into 2 Yeah, you don't even have to worry about the cosine of the angle, y'all. The answer is it asks the work due to air resistance. Just find it. Remember, let the math do the work for you. At the end of the day, you always just use the equations, let the math find it for you when it comes to scalars. You don't even have to worry about cosine of the angle, because I didn't say what's the force or anything like that.
Sorry, is it bad?
No, it's fine. Yeah, it's perfectly fine.
I'm getting 20 something.
20 something.
Yeah,
Yeah, that's because are you at the bottom or the top? That's the top, right?
that's the bottom.
Okay, so at the bottom, how fast are you moving?
Oh, it's the velocity.
Yeah.
Okay.
You gotta use the right velocity there. And that's why I put it on there. So write down your givens, y'all. What kind of energy what am I solving for? What energies do I start with? What energies do I end with? Draw a picture though. That's gonna help you. If you don't have a picture and you ask for help, I'm gonna come around and say, all right, let's draw a picture. Kind of. You have this one at a lower height than that one.
Oh,
You want to make certain, because otherwise, according to your picture, it's been a second time we'll have to picture. Otherwise,
and then also,
good news is you don't. So this is the equation for the work.
just use the work
Because it says what is the work due to it. You ever see the work due to it? You don't have to find the work. Yeah, write down your givens. The only thing new in this problem is now you got work, and this is how it shows up. This is how the equation changes if you have work due to friction. It just pops up there. It takes away energy. You're going to find that when you get your answer. You will get a negative work. Makes sense. Friction takes away energy from the system. The math will give you the negative. You don't have to assign it. Yeah, what's my final velocity? Yeah, you said you wrote it perfectly. Yeah. There you go. And this is it, y'all. This is the last problem we're doing today. We're done with it. Like, I've taught you energy. It's a really conservation of energy is really straightforward. If it doesn't make sense, trust me. You do a few problems, they're all the same. Energy I start with, energy I end with. They're great. Holla if you're stumped, but when you're done, feel free to. I'm not doing anything else. Oh, the answer is. What's the answer? Negative 14 joules. This should be pretty easy, like pretty straightforward. You should get this exact answer. Let me check if they rounded. All right, they rounded. There's the exact answer. No rounding. If you got that, you know what you're doing. Draw a picture. So that's the beginning. How fast is it? You have to point upward to velocity. Okay. Now, draw what is that? Where is it? So where's the ball? Same spot, higher, lower. So it's returning to the person. Same spot. Same exact height. Yep. And which way is it moving next? So how fast is it going? Which way is that going? Yeah, it's exactly when you draw something up on the way down, it's going down. Yeah. So in these problems, literally what does it look like? Kind of like make a movie in your mind. Great. What's given? Let's write down our givens. So we got a picture. Yep. What else?